Hello, so today we will be doing about coset of a subgroup in a group. Yesterday we have learned about subgroups, and also in the previous week we have learned about groups. So I hope you are comfortable with groups and subgroups. Again, we will encounter these throughout the semester, especially subgroups. Okay, but now let us do about coset of a subgroup. Okay, so first of all, we will need a group. Let G be a group, and then we will need a subgroup, of course. Let H be a subgroup of G. Okay, so how are we going to construct a coset? Actually, there are two types of cosets. The first one is a right coset, and the second one, it is a left coset. Okay, so let us take a look at a right coset first, and then we will take a look at the left coset. They are very similar to each other. Okay, but there's just a bit difference. Okay, so let's see. Now we are going to define a right coset. Okay, so how are we going to construct a right coset? So first of all, we take any element. You take any element from the group. That A belongs to the group. Okay, so how are we going to construct a right coset? We take the subgroup H, and then we place A on the right hand side. Okay, H, you operate with A. In between, it is the operation of the group. Sometimes it may be plus, sometimes it may be multiplication, okay, or any other operation. But again, we can easily write this one as star, H star A. Okay, but just like I said yesterday, from now onwards, we won't be writing the operation star anymore. Okay, it is easier if we just delete it. But just be careful again. Just because I don't write anything, it does not mean that it will be multiplication. Okay, so let us define this one. Okay, so a coset is actually a set. That is why I'm putting this curly bracket. So how will we define it? It will be H. Okay, maybe I'll write in this way. It is a set of all elements X which can be expressed in this way. X such that X equal HA for some H belongs to the subgroup. Again, in between, it is the operation of the group. Okay, in between it is the star. Okay, it can be any operation. Okay, so this is how we will define a right coset. Okay, so let G be a group, let H be a subgroup of G, let A belongs to G, then HA equal the set this one HA equal X such that X equal small HA for some H belongs to H. It is a right coset. Okay, okay, how are we going to define a left coset? Again, we will need let A belongs to G, the set multiply or operate A from the left hand side. So you will have this X such that X equal A small h for some H belongs to H. This one, it is a left coset. Okay, but again, in mathematics, nothing is clear until we give an example, so that is what I will do. Okay, so first of all, we will need a group. Okay, example number 1. Okay, take G. Okay, the set of integers with respect to plus. All right, so we take H to be the set of even integers, let's say, because yesterday we have found that H If we take only the even integers, it will be a subgroup. So this is what we will take: 2, 2, 4, 6, and so on. Again, yesterday we have verified that this H that we are taking over here, it is a subgroup. Okay, so now we will take A. A belongs to G. We need this. We need this A belongs to G. Okay, so which element from G I can take? Okay, so G, okay, it is a set of integers. So I will take one element from the set of integers. Okay, maybe I will take 0. Okay, it is totally your choice. This element A over here, it is totally your choice. Okay, so first let us take A equal 0. Okay, I am taking A equals 0, but similarly you can take A equal 1, A equal 2, and so on. Now we will form the right coset. The right coset, it's given by HA x, such that x equal H small a, okay, where H belongs to the subgroup H. Alright, so this one, in fact, from this line you can easily write it like this. Okay, you can write it in this way. HA, in fact, it is equal to, just write the subgroup H, so it is a set of even integers. The set of even integers, it is -6, -4, -2, 0, 2, 4, 6, okay, and so on till infinity. And over here in between, because the group that we are considering, it is with respect to addition, so that is why in between there is an addition sign. Okay, and what is A? A, okay, we are first taking A to be equal to 0. Again, maybe your choice. So what we will do, how are we going to construct this coset? We will just add each and every element with 0. Okay, add each and every element with 0. So what are we getting? -6 plus 0 will give you -6, -4, -2, 0, 2, 4, 6, and so on. Okay, so if you add each element with 0, you are getting this. So this final one will be one coset. Okay, so this one is a coset. Alright, so we have formed one coset, a right coset. Similarly, we can form a left coset, but let us look at more right cosets. Okay, now we take A equal 1. Again, if we take another element of the group, we can get another coset. So let's see. Now HA, okay, I won't write that one anymore. It's equal to that set X, such that X equal H small a, H belongs to H. Okay, I will write it directly. -6, -4, -2, 0, 2, 4, 6, and so on. In between, it is a plus because the operation of the group, +1. Okay, so just add all these elements with 1. What will you getting? -6 plus 1 will give you -5. -4 plus 1 will give you -3. -2 plus 1 will give you -1. 0 plus 1, 1, 3, 5, 7, and so on. Okay, so you will get these elements. In fact, if you analyze this coset, this one, it is a coset, this whole thing, it is just the set of odd integers. Okay, so that is what we are getting. Okay, now let us take, again we can take another element, A equal to 2. Alright, let us take A equal to 2. Let us see how much is HA equal to. Again, -6, -4, -2, 0, 2, 4, 6, plus 2. Okay, so how much will we be getting? -6 plus 2 will give you -4, -2, 0, 4, 6, and so on. Okay, so if you see, just see, this one is the coset. Again, it is a set containing the even integers. Okay, similarly we will get -6 somewhere, 8, 10, 12. okay, if we keep on adding all the elements of this set. Okay, so let us just see what we have got. If we put a equal to 0, we are getting the set of even integers. If we put a equal to 1, we are getting the set of odd integers. If we put a equal to, again we are getting the set of even integers. So what can we say over here? Okay, if you continue the pattern, in fact, you will get that if a equals 0, 2, 4, and so on, if you put the value of a to be this much, and similarly minus 2, minus 4, okay, you will get HA to be the same set. Okay, HA will be the same set, that is the set of even integers, minus 6, minus 4, minus 2, 0, and so on. Okay, so this is very important. A, even though it is taking infinitely many values, 0 to 4 and so on, but HA, it reduces to one set. This is only one set, but of course with infinitely many elements. So for all these elements A, HA, it's equal to one set. Okay. Similarly, if we take A to be odd numbers, A equal minus 1, minus 3, minus 5, and so on, and similarly 1, 3, 5, we will get HA to be the set of odd integers. 5, minus 3, okay, odd integers, okay, minus 1, 1, 3, 5, and so on. Again, even though we are changing the value of A, the value of HA, the set HA remains the same for these values of A. Okay, so if you see carefully, so how many cosets can we have? Okay, so for this particular subgroup, okay, let me see, for this particular subgroup H, okay, for this particular subgroup H, in this group G, we are having only two distinct cosets. Okay, the only possible distinct cosets are this one, this, and this. Okay, so let me just write it down. If H equal to minus 6, minus 4, minus 2, 0, 2, 4, 6, in G equal Z plus, then we get 2 TWO, 2 distinct right cosets. Okay, we are getting 2 distinct right cosets, that is, okay, the set of even integers, minus 6, minus 4, minus 2, 0, 2, and so on. And okay, this one is a coset we have found out, and similarly this is a possible coset, minus 5, minus 3, minus 1, 1, 3, and so on. Alright, so we are getting 2 possible cosets, right cosets. Similarly, we can do left cosets, okay? But with left cosets, this A should be in the left hand side. Okay, whereas the procedure is the same. Okay, the procedure is the same, but it's just that A, it is on the left hand side. Okay, so now let me define something. Index of H in G. H is a subgroup of G. Index of H in G, okay, this one is the number of distinct right cosets of H in G. Okay, so just like in the last example, the index of H it's equal to 2. Okay, but also you can replace this one by the word left. It will still be equal. Okay, so what I can say, there are a number of distinct right cosets is equal to the number of distinct left cosets. Okay, just try to find it out. Okay, do not worry, I will also give some exercises, but to be more clear, let us just take a look at another example. Okay, this one is example number 2. Again, we will consider the same group G equal H, Z plus. Now let us take H to be multiples of 3. Okay, multiples of 3, minus 9, minus 6, minus 3, 0, 3, 6, and so on. Okay, now we want to find right cosets of H. So what we will do, first we will take A equal to 0. If we take A equal to 0, how much will be HA? Okay, how much will be HA? A is equal to 0, so just add all the elements with 0, how much will you get? Okay, you will get the same thing. Okay, you will get minus 9, minus 6, minus 3, 0, 3, 6, 9. So this one is one possible coset. Okay, now let us take another value for A. Let us take A equal to 1. Okay, if we take A equal to 1, how much is HA? Again, just take H, and now instead of 0, we will just add with 1. Okay, because the operation is plus. Okay, so just add with 1, how much will you get? Minus 9 plus 1 will give you minus 8. Okay, so if we take A equal 1, HA will give you minus 8. Okay, minus 6 plus 1 will give you minus 5. Okay, and also I forgot the group, the subgroup. Minus 3 plus 1 will give you minus 2. 0 plus 1 will give you 1. 3 plus 1 will give you 4, 7, and so on. Okay, it continues. Okay, but we are not writing anything. But now let us just see, is this HA, is it equal to this, or are they different? If you take a look, the numbers, they are different. Okay, they are different. So that is why we are still having different cosets. If we still are having different cosets, what will we do? Now we will take the value of A equal 2. Again, this value of 2 we are taking from G. Okay, it's not that we are taking from H. Okay, we are taking from G. Okay, so let's see. Now what will be HA? So again, what will we do? We will add plus 2 to this subgroup. What will we get? Minus 9 plus 2, minus 6 plus 2. So that is how we will calculate. Minus 9 plus 2 will give you minus 7. Minus 6 plus 2 will give you minus 4. Okay, and minus 3 plus 2 will give you minus 1. 0 plus 2 will give you 2. 3 plus 2 will give you 5, and so on. Okay, it continues. Now again, just see, is this one, is it equal to this? Again, the numbers, they are different, so no, we are still having different coset. Again, when A equal to 2 and when A equal to 0, the numbers are still different. You can just see, this is when A equal to 2, you are getting these numbers. When A equal to 0, you are getting these numbers. So we are still having different cosets. So what will we do? We will put A equal to 3. If we put A equal to 3, now again, just calculate HA. So how much will you get? How much will you get? Let us see. Okay, sorry, where is H? Okay, now we will add 3 over here. If we add 3, so minus 9 plus 3 minus 6 plus 3, so what will we get? Okay. Okay, again dot dot dot, minus 9 plus 3 will give you minus 6, minus 6 plus 3 will give you minus 3, minus 3 plus 3 will give you 0, again 3, 6. Okay, you will have this. Now just see, now this is very important. Is this HA here, is it equal to this? No. What about with this one? Again, no. What about with A equal to 0? If you see the numbers, now they are the same. Okay, so this is when we stop. Okay, we stop when we are having a different coset. I mean the same coset. Okay, similarly, if you put A equal to 4, just try. You can figure out this one on your own. How much will you getting? Okay, and also just try, if you put A equal to 5, how much will you get HA? Okay, but again, we have taken care only of the positive values, but also you can put negative values as well. A equal minus 1, how much will you get HA? The operation between is plus, plus minus 1. Okay, again, you can put A equal minus 2, how much will you get HA? If you see, okay, the cosets, they repeat. Okay, so just like this one, when A equal to 3, it is the same thing when A equal to 0. Similarly, when A equal to 4, you will find that it will be the same coset as when A equal to 1. Okay, so they keep on repeating these cosets. So ultimately, you will be having only 3 distinct cosets. The 3 distinct cosets, they are, the 3 distinct cosets will be this one, when A equal to 3, when A equal to 2, when A equal to 1. Okay, or maybe okay, so those are the 3 possible cosets. Or even you can take A equal to 0, A equal 1, and A equal to 2. Okay, so we will be getting 3 distinct cosets. So okay, so I will just write down, if H equal multiples of 3 minus 9 minus 6 minus 3, 0, 3, 6, and so on, and G equal Z plus, then index of H in G, it's equal to the number of distinct cosets, it's equal to 3. Okay, so there are 3 distinct right cosets. Okay, so I think it is clear. All right, do not worry. Again, I will give some exercises for you to be more familiar. But now, again, let us, since we still have time, let us take a look at another example. Okay, so let's see another example where we are finding the index. Okay, so let us take G equal to, maybe Z4. Z4, addition modulo 4. Okay, just add and then take the remainder. Okay, now let us take H equal 0, 2 bar. Okay, first of all, we have to check whether this one is a subgroup. Okay, I leave that one to you. Okay, you can just see, okay, maybe I will do it, okay, or maybe not. Okay, okay, H is a subgroup. Okay, you can try showing this one, even though it's not required. Okay, but you can always try to prove that it is a subgroup, okay, by using the 3 conditions that I gave yesterday. So let us find the index of H in G. Okay, so let's see. So what are the possible values for A over here? A is from G. A belongs to G. So the possible values for A are A equals 0 bar, 1 bar, 2 bar, and 3 bar. Okay, because G, because it is in Z4, it will have 4 elements: 0 bar, 1 bar, 2 bar, and 3 bar. Okay, so now let us first take a look when A equal to 0 bar. How much is HA? HA will be H plus 0 bar, because over here it's plus. So let's see. Okay, H plus 0 bar. 0 bar plus 0 bar. How much will you get? 0 plus 0, it's 0. Divided by 4, you will have a remainder 0. Okay, so I'll write over here. You will have 0 bar. 2 plus 0 will give 2, plus 0 will give you 2 divided by 4, you will have a remainder 2. Okay, so you will have the coset to be 0 bar, 2 bar. Okay, but this is only one possible value of A. Now we change the value of A. Let us take a look at the coset H. A will be H plus 1 bar. H plus 1 bar. Okay, let us just write it down directly. Okay, I will erase this one. Similarly this. Then I will write 1 bar. 0 bar plus 1 bar will give you 0 plus 1 will give you 1 divided by 4, remainder is 1. 2 plus 1 will give you 3 divided by 4 will give you a remainder 3. Okay, so you will have 1 bar, 3 bar. Okay, so let's say this one will be 1 bar, 3 bar. Again, this coset here, it is still different from the coset here. Okay, so now we have to move on. Okay, maybe A equal 2 bar. HA will be H plus 2 bar. Okay, so let's see, let us calculate that one. How much will we be getting? Okay, so now we need plus 2, 0 plus 2, 0 plus 2 will give you 2 divided by 4, remainder will be 2. 2 plus 2, it is equal to 4, 2 plus 2 it's 4, divided by 4, remainder will be 0. Okay, so it will be again 2 bar, 0 bar. Just see, now it is repeating. This set, it is the same as this. So we are having the same coset, right coset. But just to be complete, okay, let us check A equal to 3. Similarly, if you do this, HA will be H plus 3 bar. You will be having 1, okay, 1 and 3. Okay, so over here, index of H in G, it's equal to 2 because we are having 2 distinct cosets. Okay, so I think that is clear. Okay, so now what we will do, we will simplify the notation. Okay, we will need a notation for the index. The index of H in G. Okay, index of H in G. Okay, so we will use this notation to denote the index. So I think that is also clear. Okay, for example, this one IG H, it's equal to 2. Okay, I think that is clear. Okay, so okay, maybe 5 more minutes I will continue on talking. Okay, but about groups, of course. So okay, the things that are very important. Okay, I will repeat this one. If you have a group, try to have an idea of what an identity element is and what the inverse element is. Okay, so what the inverse of each element is, that is very fundamental. You must try to master it. Just try to see at different groups that I have given, just try to be comfortable with the identity and the inverse element. Okay, the inverse always depends on the operation. Sometimes for the same element, if you change the operation, you will be having a different inverse. Okay. Also, there is this one theorem in cosets that is very, very important. Okay, theorem regarding cosets, right or left. Okay, I will do it for right, the same holds for left. Okay, if A comma B belongs to G, H is also a subgroup of G. If HA equal HB, then you can always have this AB inverse belongs to H. Similarly, you can jump from this line to this line. Okay, so many times, okay, when we continue with the real course, once you get this line, if you cannot proceed anywhere, you will ultimately jump to this line. So what I'm saying, suppose in an exercise, you have hx equal hy. Okay, where h is a subgroup, x and y, they are elements of G. Suppose if you have this line, if you cannot proceed anywhere, the next line, always remember you will write xy inverse belongs to h. Okay, so this is very, very important. Okay, we will encounter this one many times. Similarly, if we have suppose xy inverse belongs to h, and if you cannot do any other thing, okay, this is one of the lines that you must go to. From this line you can immediately jump to the line hx equal hy. Okay, this theorem I won't prove it in this semester because you have already proven it in the third semester. Okay, but it is very, very important. I won't do the proof. Okay, maybe you can refer your third semester notes for the proof. Okay, but again, it is very, very important. Okay, so let's see. Okay, so that very important theorem in cosets, and also this one. This one is also very important. You will have to remember, actually in this semester in group theory, there are a lot of theorems. Okay, some you will have to remember. Okay, I know it is very difficult remembering theorems, especially, but again I repeat, if you continue to do exercises every day, you won't have a problem. Okay, it will be just like your ABCs. Okay, you remember your ABCs up to Z because you keep on using them every day. Similarly, for these theorems also, if you continue to use them every day when solving exercises, you will get used to them. Okay, so this another theorem in cosets that's very important is this. Two cosets are either disjoint or equal. Okay, if you take any two, okay, maybe you're right. Two right cosets are either disjoint or equal. Similarly, with left cosets also, two left cosets are either disjoint or equal. Actually, over here also we can do it with left cosets AH equal BH. Then you will always have B inverse A belongs to H. Okay, or AB inverse belongs to H. Okay, I think that is clear. A inverse B belongs to H. All right. Okay, so what is this theorem? What is this theorem saying? Okay, so this theorem means that either HA intersection HB, either they are non-empty. Okay, because HA is in fact a set. Okay, we have learned that one, that a coset is in fact a set. So you can intersect two cosets. Cosets, the intersection is either non-empty or HA equal HB. Okay, so this is also very important. Either HA intersection HB is non-empty or HA equal HB. So sometimes you will encounter this line. Okay, do not worry, we will encounter these types of lines many times. Okay, once we get to the real course. Suppose you have this line. Okay, suppose in an exercise or a theorem you encounter this one. X belongs to HA intersection HB. Okay, suppose you encounter this line. Again, it looks very difficult to proceed from over here, but because they are cosets. Okay, so if I say that an element belongs to the intersection, it means the intersection is non-empty because the intersection contains an element X. Okay, so once you get a line like this, that X belongs to HA intersection HB, you can immediately conclude that HA will be equal to HB without thinking. Okay, this is a theorem. This is also a theorem that you have done in the third semester, so I won't be doing the proof. Okay, so just remember. Okay, so you will have this. Once you have an element, a common element in the intersection, okay, so the intersection of HA and HB, once you have this X over here in the intersection, you can immediately conclude that in fact HA it's equal to HB. Okay, they in fact overlap, fully overlap. All right, so this is very important. With that, I think it is enough for today.